Hello all. In this video we will look at the oracle complexity of the proximal gradient methods for smooth functions. Recall that we are considering the problem x star is equal to argmin over x capital F of x, which is defined as f of x plus h of x, where f is smooth and h is convex. The proximal gradient method in this case is given by xt plus 1 equal to prox with respect to eta t into h of xt minus eta t into gradient f of xt. Clearly, if h is an indicator function, then the proximal operator becomes the projection operator and the proximal method becomes the projected gradient method. As in the projected gradient method, the update equation requires us to assume that the proximal operator is inexpensive, or in other words, the calculation of the prox is easy. In fact, observe that if h is not smooth, then capital F of x is also non-smooth. So we are actually solving a non-smooth optimization problem, and with a stronger assumption that the objective splits into smooth and non-smooth components, f plus h, and the proximal with respect to h is easy. If that was not the case and the proximal operator cannot be readily calculated, we would have to resort to subgradient method. And we have already seen that the subgradient method has a worse oracle complexity. The analysis of the proximal method is largely similar to that of the projected gradient and subgradient methods. The gradient mapping here is defined as g eta of x equal to 1 over eta x minus prox with respect to eta h x minus eta gradient of f of x, so that the updates can be written as xt plus 1 equal to xt minus eta times g eta of xt. So for this case also the optimality condition can be written as g eta of x star equal to 0. Note that unlike the projected gradient method, minus g eta of x is not a descent direction for f. Instead, we will actually establish that it is a descent direction for capital F, which is the sum of f plus h. The two could be equivalent if h takes 0 value in its domain, such that it is an indicator function, but generally this would lead to a different form of the descent property. A few of the properties of the gradient mapping carry over from the projected case. I will just write them down and leave it up to you to prove. First is for eta 1 greater than eta 2, which is greater than 0, g eta 1 of x norm is less than equal to norm of g eta 2 of x. And eta 1 norm g eta of 1 of x is greater than equal to eta 2 norm g eta 2 of x. In other words, g eta of x norm is a decreasing function of eta, while eta times norm of g eta of x is an increasing function of eta. For L smooth functions f, g eta of x is 2 by eta plus L Lipschitz. For eta less than 2 by L, g eta of x minus eta times g eta of x norm is less than equal to norm of g eta of x. So you can see that we have established all of these properties for projection gradient mapping. It turns out that they also hold for the proximal gradient mapping. The second property is easiest to establish as it only uses the non-expansiveness, which also holds for projection as well as proximal operators. Let us start deriving the oracle complexity results. As mentioned earlier, the proofs will be largely similar with the same recursions but small differences in the way the one-step inequality is obtained. In the subsequent proofs also, only the one-step inequality will be derived. You should refer back to the notes for solving the resulting recursion using telescopic sum. For the general smooth case, so that the function f is possibly non-convex, though h has to be convex, the result is that the number of iterations in order to ensure that the minimum over t from 1 to capital T g eta of x norm is less than equal to epsilon is given by t equal to order L bf by epsilon square for eta equal to 1 over L, where b capital F is the bound on capital F of x1 minus f of x star Note that this bound matches the bound obtained for projected gradient descent, but with a modified proximal gradient mapping norm as the metric. For this and the subsequent proofs, we will need to establish the alternative to descent property. That is basically an implication of the angle property for the proximal case, which is written as inner product of x minus prox with respect to eta h of x, comma y minus prox with respect to eta h of x is less than equal to eta h of y minus eta h of prox with respect to eta h of x. Now here we will replace x with xt minus eta gradient f of xt and prox eta xt minus gradient f of xt with xt plus 1. So we obtain g eta of xt minus gradient f of xt inner product with y minus xt plus 1 is less than equal to h of y minus h of xt plus 1, where we have cancelled out eta t. Here y is arbitrary and in the domain of h. So possible choices of y can be x star or xt. The oracle complexity for the general smooth case follows from the non-increasing function property that we will now establish. We start with applying the quadratic upper bound for f, which is the smooth function. So f of xt plus 1 is less than equal to f of xt plus gradient f of xt inner product with xt plus 1 minus xt plus L by 2 norm square of xt plus 1 minus xt. Now we will use the update equation, which is that xt minus xt plus 1 equal to eta times g eta of xt, so as to obtain that the right hand side is equal to f of xt minus eta inner product of gradient f of xt comma g eta of xt plus eta square L by 2 norm square of g eta of xt. At this point we can use the descent property obtained in the previous page for y equal to xt, which says that eta inner product of gradient g eta of xt minus gradient f of xt comma g eta of xt is less than equal to h of xt minus h of xt plus 1. So substituting it here, we obtain that f of xt plus 1 plus h of xt plus 1 is less than equal to f of xt plus h of xt minus eta square 1 by eta minus L by 2 times norm square of g eta of xt. So here f plus h can be replaced by capital F. So this is the required one-step inequality. We can choose eta equal to 1 over L so that the last term is negative and can be dropped, and carry out the telescopic sum to get the required result for the general smooth case. When f is convex as well as smooth, the result is that the number of oracle calls to ensure that the optimality gap is less than equal to epsilon is given by t equal to order bl by epsilon. For the step size, eta equal to 1 over L. The proof for this case requires us to establish the alternative to co-coercivity. There are two key properties that we will use. First is that we will write down the descent property for y equal to x star so as to get inner product of g eta of xt minus gradient f of xt, x star minus xt plus 1 is less than equal to h of x star minus h of xt plus 1. This can be rearranged so that h of xt plus 1 minus h of x star minus inner product of gradient f of xt comma x star minus xt plus 1 is less than equal to inner product of g eta of xt comma xt minus eta g eta of xt minus x star, which can be written as less than equal to g eta of xt inner product with xt minus x star minus eta times norm square of g eta of xt. The second part is same as that in the projected gradient descent. We will write down the quadratic upper bound for f, which is that f of xt plus 1 is less than equal to f of xt plus inner product of gradient f of xt comma xt plus 1 minus xt plus L by 2 norm square of xt plus 1 minus xt and subtract f of x star from both sides, and then use the first order convexity condition so as to obtain f of xt plus 1 minus f of x star less than equal to inner product of gradient f of xt comma xt minus x star plus inner product of gradient f of xt comma xt plus 1 minus xt plus eta square L by 2 norm square of g eta of xt, which can be written as inner product of gradient f of xt comma xt plus 1 minus x star plus eta square L by 2 norm square of g eta of xt. So the required alternative to co-coercivity results from adding these two properties together, which yields that f of x star minus f of xt plus 1 plus inner product of g eta xt comma xt minus x star is greater than equal to eta square 1 over eta minus L by 2 norm square of g eta of xt. Here observe that the form of the property is the same as in the projected gradient method. Finally, we obtain the one-step inequality. We only need to write down the usual norm square xt plus 1 minus x star as norm square of xt plus 1 minus x star is equal to norm square of xt minus x star minus 2 eta inner product of g eta of xt comma xt minus x star plus eta square of norm square of g eta of xt, and then apply the property derived in the previous page so as to obtain that the right hand side is less than equal to xt minus x star norm square minus 2 eta f of xt plus 1 minus f of x star minus eta square 1 minus eta L norm square of g eta of xt. As you can see, this is exactly the same form as that obtained in the case of projected gradient descent. When establishing the general smooth case, we already established the non-increasing function value property. So therefore, combining these two, we can conclude that the same oracle complexity can be obtained as in the case of projected gradient descent. When f is strongly convex and smooth, the result is that the number of oracle calls to ensure that the squared distance from the optimum is less than equal to epsilon is given by t equal to order kappa log b by epsilon for step size eta equal to 1 over L. The proof of this case also starts with a similar alternative to co-coercivity property. First, we write down the quadratic upper and lower bounds for f and add them together so as to obtain f of xt plus 1 minus f of x star is less than equal to inner product of gradient f of xt, xt plus 1 minus x star plus eta square L by 2 norm square of g eta of xt minus mu by 2 norm square of xt minus x star. Next, writing the descent property for y equal to x star and rearranging, we obtain that h of xt plus 1 minus h of x star minus inner product of gradient f of xt comma x star minus xt plus 1 is less than equal to inner product of g eta of xt comma xt minus x star minus eta times norm square of g eta of xt. Now adding both of these together, we obtain the required bound, which is that f of x star minus f of xt plus 1 plus inner product of g eta of xt comma xt minus x star is greater than equal to eta square of 1 by eta minus L by 2 norm square of g eta of xt plus mu by 2 norm square of xt minus x star. So the required one-step inequality can be obtained by using this inequality. As earlier, we expand the norm square of xt plus 1 minus x star so as to get norm square of xt plus 1 minus x star equal to xt minus x star norm square minus 2 eta inner product of g eta xt comma xt minus x star plus eta square of norm square of g eta of xt, and then use the alternative to the extended co-coercivity property that we obtained previously, which yields xt plus 1 minus x star norm square is less than equal to 1 minus mu eta times xt minus x star norm square minus 2 eta f of xt plus 1 minus f of x star minus eta square 1 minus eta L into norm square of g eta of xt. Now we will drop the last term for eta equal to 1 over L, and the second term can be bounded from the quadratic lower bound on f as f of xt plus 1 minus f of x star is greater than equal to any subgradient of f at x star comma xt plus 1 minus x star plus mu by 2 norm square of xt plus 1 minus x star. So this is the quadratic lower bound. This implies that the right hand side is greater than equal to mu by 2 xt plus 1 minus x star norm square, which follows because the optimality condition says that the first term on the right is greater than equal to 0. So adding to it, we obtain the required contraction bound, which is that norm square of xt plus 1 minus x star is less than equal to 1 minus mu eta divided by 1 plus mu eta into norm square of xt minus x star, which will give us the required oracle complexity. So in summary, I was able to skip most of the steps in these proofs because, as you can see, they are mostly similar to the proofs in the projected gradient descent. In fact, the only difference was that at some points we were getting h of xt or h of x star, and that term had to be rearranged so as to get the property for capital F instead of small f. The proximal method is a very important and general method. In the modern context, it is common to see results developed for proximal versions of various algorithms rather than the projected versions. In fact, whenever you are looking at any gradient or projected gradient type method, do try to imagine how the proximal variant will work out and how it will be analyzed. Using the tools developed here, the analysis should not be too different. For instance, the proximal mirror descent algorithm can be written down with the updates xt plus 1 equal to argmin over x f of xt plus inner product of gt comma x minus xt plus 1 by eta t d phi of x comma xt plus h of x. And from the properties of the Bregman divergence, we can write down the updates in the different way as gradient of phi y of t plus 1 equal to gradient of phi xt minus eta t gt, and xt plus 1 equal to prox with respect to eta h phi y of t plus 1. So the Bregman projection is replaced with Bregman proximal operator, which is given by prox with respect to eta h phi of y is equal to argmin over x d phi of x comma y plus eta t h of x. So as usual, if h is the indicator function, then we recover the classical mirror descent algorithm, but in general this is the generalized mirror descent. Similarly, the proximal version of the Frank-Wolf algorithm takes the form yt equal to argmin over u inner product of gradient f of xt comma u plus h of u, and xt plus 1 equal to 1 minus eta t into xt plus eta t into yt, where the structure of h should be such that the y update is easier than calculating the proximal operator. A remark that we earlier showed that when we are solving the projection problem, the Frank-Wolf algorithm and the subgradient algorithm applied to the dual problem turns out to be the same. A similar duality holds when we are solving the proximal problem now. The oracle complexity of the generalized Frank-Wolf can be obtained similarly. The only difference would be the definition of the conditional gradient divergence that would be slightly different. So here it would be defined as s of f comma h of x equal to max over u inner product of gradient f of x comma x minus u plus h of x minus h of u, which can be written as inner product of gradient f of x comma x minus y of x plus h of x minus h of y of x, where y of x is defined as argmin over u inner product of gradient f of x comma u plus h of u. So that is all for this video and for the proximal methods. In the next video, we will look at the accelerated gradient method and the various smoothing techniques.